All right, this is the Unit 6 quiz. So for number 1, write the function that represents the exponential function f of x equals 2 to the x after a vertical stretch by a factor of 5 and a reflection across the x-axis. So to do this one, what we have to do is we have to remember our equation. Y equals a times b to the x minus h plus k. So we just have to remember our general form for our exponentials. So since we're starting with an equation that is 2 to the x, the nice thing is that we know what b is. B is just going to be the number 2 because that's what we're starting with. We're not changing that. That doesn't change in these ones. But our changes that we do have is we have a vertical stretch by a factor of 5. So we remember that a is going to be our vertical stretch. And then we are reflecting across the x-axis. So if we reflect across the x-axis, that means we're going to flip ourselves upside down. So that means that a is also going to have to be negative. So we're going to need that to be negative. Now in this case, there's no shifts. So both h and k are going to end up being 0. So I don't even need to write those ones. I can just write it as negative 5 times 2 to the x power. And so I've put in, not that one yet, that was show the other way. So if we start with 2 to the x, we can see what it looks like. And then if we put in 5 times 2 to the x, we can see, all right, yeah, we're going from 0, 1 and multiplying by 5 to get to 0, 5. And then if we want to flip it, we put the negative sign out front, and now we flipped it upside down. We flipped it across the x-axis. So earlier I was looking at the y-axis just for fun. So remember, if the negative sign is going to be there, we're going to flip around. In this case, it's going to be this point right here of intersection. But for this one, it's pretty cool. So we want to put the negative sign out front, and we can just flip it upside down, flip it across the x-axis. So if we want, we could double check. And that's what we do to double check. All right. For number 2, 25,000 blue trout were released into the Mehreen River for a scientific study. Function f of x is equal to 25,000 times 10 ninths to the x, represents the number of blue trout after x years. In 6 years, what's the population? So this one's actually pretty quick. So we know that x is the number of years, and we have to find it for 6 years. So we're just going to take the 6 and plug it in for x. So we get 25,000, and that makes sense because that's the starting number of blue trout. Here we've got 10 over 9. That's our b value, so we can tell that we're growing because it's bigger than 1. So that's good that the trout are surviving. And then 6 is what we're going to plug in for x. So we plug 6 in. And at this point, it's just a calculator problem, so we just throw it into the calculator. 25,000 times 10 ninths to the 6th power. We have 47,042. And again, you can round that up. You can even round that down because you could claim that we don't quite get to the last trout, but we just need to get an approximation. And that's a decent approximation. If this were a real scientific study, again, we might even round that to 47,000 just to keep the numbers a little bit cleaner. Because again, you never know what's going to happen with 42 trout out of 47,000 trout. So that's number 2. For number 3, for this function, we need to identify a whole lot of things. So we have to identify the domain, the range, the y-intercept, and the asymptote. So we got 4 parts to it. Well, the first part is nice. We notice it's an exponential because we have to the x power. So what we're going to do is we're going to say that the domain is going to be from negative infinity to infinity because that's what it is for all exponentials. For the range, we can see we're not adding or subtracting anything with the k. So that means we're either going to be going from 0 to infinity or from from negative infinity to 0. In this case, since we're flipped, we see we got the negative 1. We're going to go from negative infinity to 0. So our asymptote isn't going to go up or down, which makes the asymptote pretty easy because 0 is our ending point. Our asymptote is going to be at y equals 0. It's the x-axis. And then lastly, we have the y-intercept. The y-intercept is going to be the a value. That's negative 1 over 3. If we want, we could try it. We could plug 0 in for the x, but that's just going to be negative 1/3 times 1, or negative 1/3. And so that's it. So if I want to double check it, I can graph it. So we got negative 1/3, 5 to the x power. So negative 1/3, 5 to the x power. Turn that one off. And we can see, yeah, it's going to go on forever in the left and right direction. So that's the correct domain. For the range, it's going to go up to 0 and then down to negative infinity. So that seems pretty good. The asymptote's pretty clearly at the x or at the axis. So that's pretty good. And negative 1/3 right there is the intercept. So if I want to double check it, I can double check it. For number 4, we have a rabbit population of Springfield was 156,000 in 2016. It's expected to decrease by about 6%, 6.7% per year. So here we have to realize that we're decreasing. So we're going to have some decay. So we start off with our exponential decay function. So our exponential function is y equals a b x minus h plus k. All right. So if I want to write this out, I'm going to see what my starting value is because a is the starting value. So I'm going to get 156,000. So that's going to be a. So 156,000. B, I have to be careful because for B, since we're decreasing by 6.7%, B is going to be 1 minus 0.067. So remember, we always have 1. We get the minus sign for decay. So our decrease here is going to be the minus sign. And then 6.7% is 0.067. So 1 minus 0.067. Here we have the choice. I'm going to do x minus the 2016. You don't need to do the 2016. You can always count years after 2016 if you want. I'm going to do that, though, since they give me that value. So that's going to be h. H is going to be the starting amount for the x's. So we're starting at the year 2016. And then k, there's no k. There's no shift. We don't have any vertical shift or anything. So k in this case is 0, so I'm not going to write it over here. So this is just going to be my final equation. It looks like it's pretty big. But again, we've got big numbers. We got some big decimals here. We're doing it with the whole year, so we have a little bit extra there too. For part B, we have to figure out what the population is in 2036. So 2036 is an x value. So what we're going to do is take the 2036 and just plug it in for that x. And again, from there, it's going to be a calculator problem. So 156,000, 1 minus 0.067 to be 2036 minus 2016. And we get our value 38,972. All right, 38,972. And again, since we're dealing with a large population, totally fine around that, even to maybe 40,000. And this does make sense because unfortunately our rabbits are decreasing, so we should expect to have less rabbits than we started with. So that makes sense because we started with 156,000 and we ended with about 40,000. So our rabbits are going down in this case. All right. For number 5, what is the average rate of change shown on the interval from 0 to 3 in the function shown on the graph? So with this one, we have to remember that average rate of change is just asking for the slope. So we just have to find the slope between these two. So the slope, that was a really bad angle. We're going to go over and up because we can say that the slope is just going to be rise over run here. If you want, you could do, y2 minus y1 over x2 minus x1, f of b minus f of a over b minus a. But since they give us the picture, I'm just going to count 1, 2, 3. 1, 2, 3. It's just 1. So that's all there is to that one. So it's just remembering an average rate of change that we've had back in Unit 1 and Unit 2. We're just using that one more time. So that's what we got for that one. It's just asking for the slope. For number 6, Steve invests $1,500 in an account that earns 4.1% annual interest compounded continuously. So here's the trick, is we have to recognize that it says compounded continuously. And that tells us that we're going to do the A e to the RT equation. So we're not going to use the big one for this one because we're doing continuously, and continuously uses the e. So we're going to use the one with the e. And from here, we just fill them all in. So we're going to invest $150,000. So that's our principal. So that's going to be y equals 1,500. E stays as e. So e is just a number, just like pi. R is our interest rate. So we got to find our interest rate. Interest rate is going to be 4.1%. So 0.041 for 4.1%. This is the R. And then T, we're going to do it for 10 years. So that's going to be T. We may as well make this A or P if you like the PERT equation. But we've got 10 up there. And again, at this point, it's a calculator question. We throw it in the calculator. So 1,500 e to the 0.047. And let me double check to see if I got that interest rate right. 4.1, not 4.7. All right, so 2260.23. And that's going to be our final result. So again, we want to go to two decimals. I guess we have to go to nearest dollar. So 2260. I would go to the nearest cent because it is a money question. So, but they want to the nearest dollar. So 2260. So that's pretty good. So after 10 years, he's made, looks like $760 just by doing nothing, just by not using his money. So decent. But that's what we got for number 6. For number 7, Mike is going to invest into a different account. It's going to earn 5.3% interest compounded monthly. So here we see we have compounded monthly. So that means that we can't use the one with the e. We have to use the big equation. So y equals a or p, 1 plus r over n to the nt power. All right, and again, we're just going to fill it in. So the amount we start with is a or p, if you like that to be p. So 5820. In parentheses, 1 stays as 1. The interest rate we have here is 5.3, so 0.053. And now we have monthly. So monthly is going to tell us what n is. That is r. So n is going to be 12 because there's 12 months in a year. So we're going to put 12 down here. And then in parentheses, we get to put 12 in again for the n. And time, well, we don't know how many years that we have. We just have to write an equation or write a function. And so that's what our function looks like. So time just stays as t. So that's just a t. All right. And then part B says, what's the value of the account after 8 years to the nearest cent? So again, here 8 is a time. So we're going to take this and plug it in for the t. So y equals, I'm just going to write it all in black, 5280. 1 plus 0.053 over 12. 12 times 8. And again, this is something that we have to put in the calculator, so we just go to the calculator. 5820, 1 plus, I forget the interest rate, 0.053. 12, oops, to the 12 times 8 years, and we get 885.02. 885.02. Because again, this time we're going to the nearest cent. So that's what we got, to the nearest cent. All right. And so that's it. So you can see there's a lot of calculator, but calculator is like the second part. You have to actually do the first part by coming up with the equations. And number 8 is no different. So 1970, population of a small town is 5,700. Population is decreasing at a rate of 3.2%. So again, we can see we're decreasing here. Per year, write an exponential decay function to represent the situation. So Again, we're decreasing. It's a per year thing, so we're going to use the same equation as before. A times B to the x minus h plus k. So y equals our starting amount A is 5,700. Here again, since we're decreasing, that means that B is going to be 1 minus 0.032. X is going to stay as X. H is our starting X value. That's our starting year. So 1970. And again, you don't need to put this one in. You can count for years after 1970. And then K again is just going to be 0. We're not going to have anything for K. And that's it. Just says write the function. So that's it. That's the function. So again, it would also be correct if you didn't have the 1970 there, because you can also choose to count years after 1970. But that's that one. So just write the function. Number 9 at 7, Ferdinand pours a cup of tea whose temperature is 212. The tea starts to cool to room temperature, 72 degrees Fahrenheit. At 7:02 a.m., the temperature of the tea is 204 degrees Fahrenheit. At 7:15 a.m., the temperature of the tea is 192 degrees Fahrenheit. Ferdinand will drink the tea when its temperature is 175 degrees Fahrenheit. Use exponential regression to find a model for the temperature of the tea. So right here, they're telling us what to do is to use the regression, and we just have to throw that into the calculator. We're going to do y1, if you're using Desmos, tilde a b to the x1. And we're just going to go like that. I think I'm also going to do this not in terms of actual times, because again, if our time is going to end up being past 8 o'clock, we're probably going to get pretty confused. So what we're going to do is we're going to do minutes after 7. And so that's going to give us all of our values that we want. So we're going to go 0 to 12. So I have to make a table. And then I believe it's 7:02 was the next one. And we're at 2:04. And then 7:15 was 192. And 15. So, I'm not putting the 7 because I want it to be 7 o'clock, not 700. And remember, time is not really base 10, so we can't really do that. We don't want to have that in there. Let me zoom out so I can actually see my numbers. I want to see my dots. I got to go all the way to 212. So there's my dots. Okay, so it looks good. It looks like we're decreasing, which makes sense because our T should be cooling off. Y1 tilde A times B to the X1. All right, so let's see what we get. That doesn't look that great, but that's what the model's given us. We have an R squared of 0.92, so it says it's pretty good. So Desmos likes it. All right, so let's grab our equation then. I'm gonna cheat by grabbing it. You can notice it doesn't exactly go through the dots, and that's okay. All right. Okay, so our equation then is going to become y equals A is 209.452. B is 0.994069. And then x just is going to be x. So there we go. So that's my exponential regression. I found the model for the temperature of the tea. For part B, it asks, when can Ferdinand drink the tea? Well, he wants to drink it when it's 175 degrees Fahrenheit. So we want 175 to equal 209.452. 0.994069 to the x power. Now, I'm going to just say probably solving this graphically is going to be the best, especially because we already have the graph. So I'm just going to type in, we want y to equal 175 and see that it's right here. About half an hour, so 30.2 minutes. So if we want to be very precise, we can say about 30.2 minutes after, but that doesn't answer the question. So it says, when can he drink the tea? So that would be at about 7:30. All right. So for number 10, what's the inverse of the exponential function y equals 4 to the x? So what we can do is we can switch the x's and the y's because we're doing an inverse. So we want x equals 4 to the y. And then we just need to make it into a logarithmic equation. So let's rewrite this as 4 to the y equals x. And that's going to give us log base 4 of x equals y. And that's it. That's our entire logarithmic equation. Again, if you don't like doing this, again, what we could do is we could say we're taking log base 4 of both sides, and that'll work out perfectly well. So that's number 10. That's our inverse. For number 11, estimate the value of ln of 22 to 3 decimal places. Well, that's pretty easy. ln of 22, 3.091. That's it. Remember, on your graphing calculator for your TIs, there is an ln button right on the face of the calculator. You don't have to go hunting for it. For 12, write the logarithmic equation log base 5 of 125 equals 3 in exponential form. Okay, we can do that. All right, I'm done. That's it. That's all it is. You could also choose to exponentiate both sides to the 5th power. So you could go 5 and then 5 and get to the same answer. For number 13, what's the solution to the equation log base 2 of 3x plus 1 equals 4? Round to the nearest thousandth if necessary. Okay, well, let's go ahead and solve it then. So we've got 2 to the 4th power equals 3x plus 1. So 16 equals 3x plus 1. 15 equals 3x. Divide both sides by 3. We get 5 equals x. Okay, all right, seems good. Let's double check it. Let's make sure it's good. So it's log base 2. So I can't type it, actually. Well, I could type it, but I'm going to bring up the log base because most people will probably come all the way down here looking for the log. Where's our log base? Where's our log base? Where's our log base? Log base, log base, log base. It's in the calculus section. Interesting. All right, log base 2 of 3x plus 1. And we want that to equal 4. Let's turn this one off from before. We don't really need this one anymore. Let's go home. All right, and they intersect F5. So it looks like we got it right. So if I want to double check, again, I can double check it with the graph. Actually, I think a lot easier just to solve it by hand than to actually do the graph. So that's 13. And then 14, which is the last one, which of the following have been evaluated correctly? Select all that apply. Well, for the first one, if we change it, we would get 2 to the 5th equals 32. 32 does equal 32, so I'm good with A. Part B, 3 to the negative 3rd equals 127. This would be 1 over 3 to the 3rd equals 127. So that's 1 over 127 equals 127. I'm not picking that one. That one doesn't look good. Remember, if there's no number after the log, that's log base 10. One of the log rules is that if the base is equal to mantissa, if these two numbers are the same, we're going to just become 1. 1 does not equal 100, so we're out there. For part D, ln of 2 equals 1.6931. I'm pretty sure that's not true. I'm pretty sure ln of 2 might be about that number, but let's just double check it to make sure. Perfect. We'll change ln of 2 to ln of 22 to ln of 2. No, not even close. Look, there's a whole bunch of decimals there. There is not a whole bunch of decimals here. That one's out. I'm not picking that one. And then for the final one, we've got log base 6 of -1 equals 0. So we would have 6 to the 0 equals -1. 1 equals -1, which is not true. Also, remember, you can't really put negatives inside of logs, so you're kind of done for there, too. So that's it. That's all we wanted to check. If we really wanted to, we could throw some of the other ones, like we could throw the red one and the blue one, even the purple one into the calculator if we want, but I don't think that's really necessary. So I believe that's about it, right? I guess that's it. Yep. So that's everything on the quiz. So again, the big highlights are just knowing those exponential equations. So there were two of them that were kind of important. Let's go back up to where we did those. That would be, well, this one right here. So our first exponential equation is just our general form for our exponential. But again, that's the a's, the h's, and the k's. And then the other one that was pretty new would be our compounded continuously. So again, the key to use this one versus the other one is it has to say continuously. If it says continuously, you're using the one with the e. If it doesn't say continuously, you're not using the one with the e, you're using the big equation. This would be the big one for the interest. All right, so that should be about it then.